Hi, thank you very much. So my name is Ravishankar Borgaonkar. I work as a research scientist at SINTEF in Norway. I recently moved to Norway from UK, previously with the University of Oxford. And this is Altaf Shaik, who is currently doing PhD at TU Berlin in Germany. That's also called SECT, but that means security in telecommunication, not this SECT. Okay, so that's the SECT, different department. And today we briefly talk about 5G security, but the point was first to cover radio part, but most of the time people have interest to also listen about what new has been done on the core network, or what is this controversy going on, people talking about 5G and different thing. So we try to give this highlight also in a short period of time, and then we focus on some vulnerabilities which has been we discovered and been about to fix, for example. So I would skip the about me or talking more about what we did in the past, anything, but I will just say that he's doing a PhD, and I started my study on mobile telecommunication, and I can proudly say I studied in KTH in 2007, so that's like 12 years back. So I learned 2G, 3G in Stockholm itself in 2007, and since then I'm still working on the same stack. So we just straight ahead go to the 5G now. How many people know 5G in the room or been working or something? So a couple of people. So I will try to speed up the things rather than speaking on what is new feature or marketing stuff or anything. I will just say what exactly we're going to see this year and what we're going to see after a couple of years. So we're going to have billions of devices trying to connect to each other, or maybe to the cloud, or maybe you will use those devices as a personal devices. And this will keep growing. And since 2009, this is already, and some countries have started to deploy 5G networks. So we have a 5G base stations being deployed as a pilot or something. Right now we know. And these networks are basically, or these base stations are connected to a 4G core network. That's the existing 4G network we have. And then that's what we called non-standalone mode. That's one type of 5G, which we are seeing in the world. And the second type, what we will see many operators are being deployed slowly. Some are already trying that. But that's the second time which we'll have a 5G towers being deployed, and then we have a 5G new core network. And this is basically called standalone mode, and that we will see maybe next year, for example, or there are some Asian operators are trying this approach as well, for example. So it's there are different strategies, the way you deploy those networks, depending on the cost and deployment types. But this is just to give you a start. And what is the problem people are talking about, basically, about this second type of network, which is called standalone mode, because this is pretty much evolved networks. Many things has been drastically changed. And in next couple of slides, I will try to cover that up. And why actually 5G is becoming a problem, or why people also says this will be a bug issue. It's just that now, if you look at this picture, we have 100 Mbps as a broadband speed. So I live in Norway now, still I get 50 Mbps. But when I was living in Finland, I had a pretty much higher speed than what used to get as a broadband speed. But roughly average, we have 100 Mbps. And what 5G is being promising nowadays is like a 5 Gbps. I'm still realistically skeptical about that, because if you look at some live test, people were getting 1.2 Gbps in Korea or Switzerland when they deployed the network. But it's still better than the wired. So can you imagine after 10 or 15 years, will people start digging more ground to put the cables, or every device will use wireless? So you see the comparison between where we are moving. So next 20 years, maybe everything will be wireless. And we no longer use broadband connectivity, which barely giving you 100 Mbps. You can argue me saying that, fine, we can get the gigabit connection or something like this, but still, how much gigabit you're going to consume, that's also another kind of a trade-off. So basically, we are making this 5G as a national critical infrastructure already when we're looking at 10, 20 years, that every device literally going to talk over the wireless channel, right? And this is what the network had some new changes has been made. And we try to just scratch the surface about how this architecture looks like and where are the problems, and we give some example of those problems. Then you can just make a logical conclusion yourself, what is this fuzz about on 5G security. So when we see the network, we classically divide in two styles. I will just try to keep minimal and simple. So this is a very abstract level view. So don't count me saying that, okay, you are the wrong guy who represented different architecture by standard or 3GPP. Literally, trust me, you will no longer understand those like 10,000 documents with different abbreviations or anything like this. I'm trying to avoid that. So you have a radio network, which is basically we call radio access network. So that consists of your mobile phone and the tower, which you see in the buildings or surroundings area. You have the towers, right? That's the radio access network. And then you have a core network. Core network means there could be a building of Telia or Telenor where you will see there all the servers are being there, which are being used for call switching or to support the call services. And what has been happening since last 30 years, we are getting development into the radio part as well in terms of speed, what you get with wireless, but we are also getting different kind of improvements with the core network. And slowly, we are moving towards the internet. So it means that classically we used to have special signaling protocols in the core network. Everything was proprietary, standardized dominated by few companies in the world. And slowly it's moving, some new companies are coming up in the game, and standard is coming towards the internet style of protocols. And this is what we are seeing now. And this is what you look now, the 5G architecture. So this is clearly a 5G architecture by the standard. I'm not going to explain those blocks, for example, what you have. But this is a diagram to tell you the significance. Because in terms of a wireless, what is important, first point is, when you make a mobile phone call or when you use your internet data for mail, what is the encryption starting point and what is the encryption ending? Because end-to-end encryption, that's what we talk about, right? And now imagine when you make a 5G phone call, let's talk about where the encryption starts and ends as per the 5G. And this sets the critical task, actually, because this you can decide whether it's an end-to-end or not, 5G. So you decide yourself. So what happens if you see this figure? Do you see the cursor? Yes. So this is basically a mobile phone you have when you have 5G. This is called UE, user equipment. And this will have a SIM card, and nowadays we are moving towards the new SIM card, which is called embedded SIM card. And this G node B means the base station. And in 5G, they decided to split this base station into two types, which is called centralized unit, and one is called distributed unit. The reason behind this distribution, let's assume that this area may have a 4G base stations, like a 10 base stations to serve this ½ kilometer area. So in 5G, we may need 20, because we need to double the number of base stations to serve the capacity and speed. And it may be case that these base stations may be deployed on the street lamp or on the bus stop or somewhere with unsecured location, basically. So you can split the network into CU and DU. And what is being happening, actually, if the operator doesn't deploy a CU-DU model, so basically your encryption starts on a mobile phone and ends on a base station. So it means if somebody compromises the base stations, you're going to get plain text traffic. Okay, and this is the case with even 4G network. And this is what people ask me, what is the best network you see in terms of radio? Actually, the 3G was the best, which we're about to kill. Because in 3G, your encryption was never ending on a base station. It was partly ending on the core network infrastructure. It means it was ending on a physical node, which was somewhere in the building, which is secured location. So your call was ending there, but not in 5G. 5G, it will end on the base station straight ahead. So if you compromise the base station by any means, or whatever it is, so basically you get plain text traffic there. Of course, it's encrypted from there, but it's a different IPsec tunnel. So it's, again, the way you compromise or take over the box, for example. And what the new things has been changed, again, this is basically a core network. Now, we have moved towards the service-based architecture. So this is the most promising change part in the core network. It has been evolved. So the 5G has adopted service-based model, service-based architecture. So, and the reason behind this, I mean, I'm not going in detail, but it just service has to be deployed so much fast and quickly. And that's what they decided to use a new service-based architecture in that regard. And the point is, this is somewhat, I will come back to this point. So why this people say about why this has been changed or evolved. So basically, this is a combination of few technologies. And this is what it makes interesting. So it's a combination of cloud computing, programmable networks, NFV, or mobile edge computing. So we are trying to adopt the cloud-based architecture now into the core network. So it means that we are moving towards the virtualized world, or I would say the telco is trying to adopt the virtualized network functionality. It means that we will have the same kind of a hardware which running on different kind of virtualized softwares, which we also use in cloud computing, for example. So this is being adopted into the network now. So you no longer have a physical devices running somewhere. It could be a cloud, basically, which running everything. So if I give an example, if a Telenor or Telia has a infrastructure running in somewhere in the building, which is physical infrastructure, IT infrastructure, now this can be going to the cloud, which could be their own cloud, or they can rent somebody else's cloud or whatever it is. So that's what there will be a less physical separation on that regard. And what has been changed if I compare with the existing network, so we used to have a separated core network and RAN network with 4G networks. We had a dedicated, literally dedicated hardware to run the core network component. We also used to have, as I said, proprietary protocols when we use 4G inside signaling. So many people have heard about SS7 signaling attacks or something like this, right? So these are like a proprietary protocol which also been exploited, but that's the goal. And this was difficult to modify services when the customer demands there is something new they want. So it takes a long time to adapt for any companies to provide new services because you have to change many components, and this was not that flexible. And now with 5G, now we have a less separated core and network. It's still separated, but logical separation. And I think the organizers of this conference were smart enough to arrange all the cloud security talks in the morning. And now we're going to separate those in the cloud infrastructure, and we already saw some attacks on the cloud. I mean, this is just a reference, for example, how much separation you made in that regard, and configurable software and hardware. And the funny thing is now, they have replaced the SS7 signaling protocol with REST-based Java API. And you imagine any attacker now who wants to attack SS7 signaling, he has to just literally read everything about SS7. It's a proprietary protocol, or it's not much documentation available, not many tools available. He had to read those documents, make an attack or something like this to exploit in real time. And now here, attacker just need to learn the REST-based Java APIs, which everybody is working or useful of the knowledge. And those REST-based APIs basically has to be secured with TLS and SSL. So we are moving towards that area with core network. And this is pretty much challenging for the mobile operators to really secure this. And what the problem is basically coming, now we will have an increased attack surface with what we say. But I think so far we are doing research. We try to use a smartphone basically as a, it's a smart device, but it's a slave device. Many people say smart means dumb security, but in mobile world, smart means slave. Because mobile phone is smartphone, but it's a slave basically, because it just acts the way your base station says. And that's what the fake base station attack has too much priority and has been given attention in 5G to prevent fake base station attack. Any fake base station comes and asks mobile phone, hey, let's talk plain text. I don't use encryption. So your mobile phone says, okay, fine, let's use plain text. He has no role saying that, no, I stick with A53 or a stronger encryption. He has no role of saying. And the whole design has been followed the same approach. No change at all. So there is no negotiation it has on key exchange or anything. So that's what we'll have beating down attacks as usual, because as long as you can lock your phone. So how many people have a phone which they can lock on, let's say on 4G? Can you lock your phone on 4G? Yes, and you rely on the Android function that it really locks it, right? Because this is a physical lock separation, for example. But very few phone has this, and it's not mandatory that every vendor should actually have that feature on your mobile phone. Very few phone give this feature, or some phone will just say 2G, 3G, 4G, or you will just have a 4G and 3G, for example. So very few phone have this. Then we have a denial of service attack, wireless as usual, and tracking and interception. Somewhat it has been fixed, but not completely. With 5G core network, it's just a summarization, but as we are moving towards virtualized world, so as usual, then we have a cloud security different aspect, virtualization as well, because then you're gonna virtualize many network elements. And you'll have a third-party APIs. For example, now you deploy the cloud services, you need a firewall or antivirus, and you need to give a different access with the tokens to a firewall deploy vendor. Could be any vendor or something, so you need to protect that. You don't expose many elements of a cloud to the third-party vendor, or those kind of separations, you have a problem as well. This is classical problem on this regard. And this is one example. Basically, I tried to give you what it means by increased attack surface. So what people are trying to say basically, so we'll have a virtualization. It means from base stations, your data may go to the edge cloud. It could be a data center, for example. So before it goes to the core network, it goes to the local data center, or it's edge data center, what we say. And basically, they will have a clear separation of services. So let's assume that on the right side is a cloud-based core network or one data center of element, and they have a different cloud instances for different services. And the first is for gaming users, what this marketing is about. Some game users can have a high-speed dedicated service whenever they use 5G service for playing the games. One is for smart grid or something, and one is for normal users. So we can replicate these services with emergency services or whatever you name it, different classical separation. And of course, they assume that you will protect all these instances using hypervisor security. And it's like we have a bulletproof hypervisor security, and that's what we say. There are many commercial providers. They try to give you the protections on those elements. And now we have to ensure that an attacker, when he is using any end devices or somebody is compromising the base stations which are at unsecure locations, they may not be able to attack this cloud part, or maybe this whole block is not connected to the internet, that you will have a remote attacks which are coming over to your cloud interface. So see, this is like you are opening up the, or adopting the internet cloud-based technology, so it's you're gonna at least realize that this will come anyway. And just to give a significance of now, if I really wanted to compromise some of this element, I give you one classic example, really classic example. This was the year of 2002, something around that, if I'm not wrong, or 7 something. Okay, how many people know Greek wiretapping scandal? So yeah, some people know. So very powerful organization. Back in 2002, compromised one unique server in the core network. Why it was unique? This was called a lawful interception. So when you deploy mobile network, you need to provide lawful interception capability to government. And this is mandatory. This is standardized interface. And the way it has been built, it's quite secret on, we don't know what exactly it runs actually. So it's like a special interface built on, I don't know, Linux or whatever the system is, for example, right? So somebody actually was able to build a malware for this system. And the malware was so nice that somebody just put the USB stick or they reinstalled the whole software on this machine. And this machine basically is like a secret police has a live tapping interface. You just feed a number and you get all the call records live, literally live. And actually they compromised this machine. So they got some mole inside the employee, asked him to give a software or something like this, and he installed the software. And for a couple of months, the call record of a Greek prime minister or some prime minister was continuously monitored. And luckily, there was this one Swedish company engineer, he came to investigate what's going wrong, and he figured out that this is not the software which is provided by a Swedish company. And so my point is, the biggest telecom vendor in Europe was not able to recognize this attack at all. So it was the engineer who came to figure out why this traffic is weird. I mean, he checked that what is the problem. So after 6 months, they recognize what is the problem. And actually, it has a nice architecture and diagram and everything like this. So imagine this was a proprietary software which very few people know, and it was being compromised that time. And now we are talking about, we're going to build this block into the cloud. Okay, now like this kind of a blocks, we're going to build into the cloud, and we're going to say that we protect this with hypervisor, or whatever it is. And now imagine now how many nation-state actors we have and how you're going to protect this kind of infrastructure against these attacks. So this is one example of a tip you can compare with the logical reasoning, the way we are moving towards which side. And then the second, we have sometimes we do configurational mistakes. Like this was one example of you do configuration mistakes. So one company in Belgium was doing pen testing, and they were just fuzzing some packets actually. And one of the core component block of a network, core network actually, he received some bad packets in Norway because it is roaming, all operators are connected to each other. So by mistake, he received some fuzzing packets, and the software got crashed just by a few fuzzing packets. And it was not able to recover for 2 days. Again, that involves the biggest Scandinavian company in itself actually. So, but my point is, you don't have those software which are being properly secured, properly pen tested, or fuzz, or whatever it is. Now, you're moving those blocks into the core network, protected with REST-based Java APIs and authentication tokens. How many people really do a bug bounty and found vulnerability on REST-based Java API token authentication bypass, something like this? You just name it. You just find endless, for example, like those examples. I'm not saying that it's difficult to achieve, But it just, the point is, look at where you are moving and the way you are controlling the data. And then we also have the Snowden kind of incidents where people talk about they had a master keys of every SIM card being like they compromised the Gemalto and they got all the keys and everything like this. And now we have an eSIM. eSIM means you never can get out of your mobile phone. So it means when the mobile phone is being manufactured in China or anywhere it is, it will become equipped on your mobile phone, and you can't take out the SIM card. And you may have heard last 2 weeks before, there was a company who discovered a problem with SIM card. Somebody can send you a command, and it just executes in the SIM card, and it sends data back to the server. This was like a standard vulnerability again. And as an end user, I mean, I don't have a control on my mobile phone. I can't take out the SIM card now. So it's quite problematic in that scenario. And you just trust them blindly what's going on, happening inside. And this was not new. The Snowden document also had a malware for SIM card as well, like a Java applets with SIM card, for example. So this is like, anyway. Then we have a denial of service attacks. This is quite obvious, and this is not really new, but just to mention, because assuming we have a 1 Gbps at least speed, realistic way, so you have to protect against denial of service attacks with 1 Gbps on the radio side as well as on the internet side. So we'll have a new distributed denial of service protection tools or techniques. So don't get surprised that there are many companies buying like this, especially the telco providers. So this will be a nice business for those companies. Now coming back to the point, this is about the core network. I mean, we touched some surface. Now we'll go into the main content about have we solved the radio problems of 4G and 3G and 5G or not, or whether the IMSI Catcher really work or not. Now we dig into this type. So what exactly this about? There are two types of, first of all, when we say IMSI Catcher for this talk, we only talk about locating a user, tracking, for example, but no interception. Because IMSI Catcher has a definition that you track, also you intercept. So we're not talking about interception, okay? Clear? So no data encryption, no data interception or call interception. It's only about identifying particular user in the area, 5G user, and also the tracking for some time. But we also now talk about monitoring the user. So we have a third element of monitoring which hasn't been done with IMSI Catcher. And there are two types we do basically. We try to exploit some radio protocols, but we also try to exploit ACA protocol, which is basically a main authentication protocol in 5G. So I will hand over to Altaf, and he will explain you the first vulnerability, and then I will explain you the second one. Yes.
Okay. So that now you have learned something about 5G, so let's look what we try to exploit regarding the protocols in 5G, mostly on the radio access side. So we try to see that, I mean, if you have seen the previous slide, so you saw that IMSI is actually encrypted in 5G. So this is kind of an optional feature that whenever the device is sending IMSI or IMEI to the network, so these identities are actually like encrypted. So these are like the unique identities that the SIM card and the phone has it. So basically like you use them to identify a user or a phone. So we know that, okay, these are somehow encrypted, and then we started looking what else we can try to actually like fingerprint users or fingerprint devices. So we started looking deep into protocols, and then we came across something called capabilities. The word UE means nothing but user equipment. So it could be a smartphone, or it could be any M2M device, or any device that has a modem inside and trying to register to the network can be called as a UE. So we came across this thing called capabilities. So when I talk like capabilities of a device, it doesn't mean the processor or the speed, the RAM. It doesn't mean that. So it's the modem capabilities. For example, the capabilities can be like two types. Like we see, it's like core network capabilities. Then the second one is the radio capabilities. Like the capabilities in the sense like what kind of frequencies it support, or what kind of like physical parameters does it support, carrier aggregation, or the new MIMO technologies that actually bring speed to LTE. So these are some of the things that what actually capabilities mean. And then if you take new modems, for example, like the ones which will come in smart cars or like automated cars, so they have something like V2X capabilities. So these are actually defined in the modem. So these are designed and then defined, and then everything has a value. So either it supports or doesn't support. Like you see here, like it has two different capabilities, like core network, then radio. Core network, like basically you can call what kind of like security algorithms it supports. So it can also support null algorithms, which means that all the keys are nothing but 0. So there are sometimes like the device is using null encryption algorithm, maybe during emergency mode. So yeah, so if you go a bit more detail, like, okay, this could be different kind of capabilities. It also supports, for example, if it's a smartphone, obviously it's supporting 3G and 2G. So if you look a bit detail, like, so this is nothing but a Wireshark trace. So it says like mobile station class mark 2, which says that the device supports 2G, or it supports like GPRS. Then mobile station class mark 3, which mentions that it supports like 3G. And then you see below, it's something like voice domain and UV usage setting. So this is something that's very specific to phones, because obviously we use phones to make phone calls. So that if you also like find modems in vending machines, they obviously don't make any kind of like phone calls. So this kind of like capability is actually disabled in vending machines. So some 5G specific, like V2X capabilities, then cellular IoT, like narrowband IoT chips. So these are something which will come already in the market, but they will be a bit more like, you will find them more often, like so. So these are some of the radio capabilities, like what kind of measurements it can do, what kind of like frequency bands, then RF parameters. Then something very important is like the category. If you have like a high-end smartphone, for example, like iPhone 10, obviously, normally the category is like Cat 16 device. If you have an iPhone 5, which is like kind of very old, this could be called as like Cat 6 device. So the higher the generation of the device, then the higher the category. So these are actually, so normally when you turn on your phone with the SIM card, so it tries to register the network. So basically, like when it's registering, it's actually sending all these capabilities to the network, so that network knows what kind of device it is. And then based on that, it can actually prepare the service or like allocate the kind of service for that. So if you look there, the core network capabilities there are actually sent to the network before doing authentication. So then that's okay. Then we come down a bit like, okay, authentication and security is done between the device and the core network. And if you go down a little bit, like there is something called radio access capabilities. If you look clearly here, like the radio access capabilities are sent prior to OTA security. So OTA is nothing but over the air. So basically, the capabilities are sent in both cases, like prior to establishing some kind of security there. So this is what makes it interesting for us. So we thought we could do some passive and active attacks in this case. And then this is the major flaw. So we started to like look more, what can we do with these capabilities? So we came up with 3 types of attacks. The first one is like MNMAP, then also some beating down attacks, and something, a power drain attack that's especially directed to IoT devices. So we built a setup. So we were like planning for some man-in-the-middle attacks, not only like just passive, also an active man-in-the-middle. So where we need a rogue base station plus also a phone. So this rogue base station actually receives traffic from a victim phone and then forwards it using a fake UV to the real network. So you're acting like a relay. So we use 2 software-defined radios and 2 laptops, obviously, which are running different base station and then phone softwares. Usually we use the software from SRS LTE. So this is an open source cellular stack. So we try to use it, but we have to extensively modify them so that we have the whole man-in-the-middle setup. So this was like pretty complicated to do, but still somehow like we try to achieve it. And then we try to do some attacks with like real devices and also like on the commercial networks. But I think we took like extensive care so that we do not mess up with, yeah. Like the first one I was telling, the MNMAP. So we know the word like Nmap. So this is something very common in the internet world. So you use this tool to actually find out live hosts on the network and then what kind of ports are open or what kind of services they are running. So this is what we are doing. So we thought we can do something similar for the mobile networks. So somebody puts up a base station and then try to find out what kind of devices are in the surrounding. Because like we will have thousands or billions of devices using modems. So it's quite common that we want to have this kind of tool. So we call it like MNMAP, like mobile Nmap. So what we are trying to do here is like we are trying to find the maker of this device, then the model, then the operating system, then what kind of applications it's running, then what kind of versions they're using, all based on the capabilities that we try to passively capture from the phone or actively get it from the phone. So this is the kind of tree that we built. So first, we actually start with identifying the baseband of the device, then the baseband manufacturer, like what kind of model it is, then who actually made this baseband, then if it's a cellular baseband or if it's a cellular IoT baseband. If it's a cellular device, it could be either a phone or some other device. If it's a phone, then it's Android or iOS. Then if it's Android, what kind of Android phone, like Samsung, Huawei, and if it's an iOS device, it's an iPad or iPhone, or so then what kind of operating system version it's running. So we try to like deduce all this kind of information from the capabilities that we received. And if you look the other side, like if it's a cellular device, but it's another kind of device, it could be a car modem, or it could be a modem that's sitting in a USB stick or in a laptop. So we try to find out all this information. So you can ask me, like, why is this identification or like this kind of fingerprinting possible? Because like normally these capabilities are designed by the baseband manufacturers, for example, like Qualcomm, Samsung, MediaTek, Huawei. So there are like many manufacturers like who actually design these capabilities. So it's not really mandatory to implement all these capabilities. So it's optional to implement some of them and to not to have some of them. So some of them can disable some bands, some can enable some features. So the thing is here is like baseband vendors implement these capabilities differently. So there is some kind of like scope there to identify each of them based on their implementations. Then the second one is like each target applications require enabling or disabling of certain capabilities. For example, like if you take a GPS device, a tracker, so it always needs this location feature on. Or if you take like a smart car, it needs these V2X capabilities like activated. Or phones, they need always this voice calling capabilities. So what we did, so before actually trying to identify devices, like we wanted to build a huge model. So we collected like maybe up to 80 different devices. This includes like laptops, cars, USB sticks, routers, some devices from the military, some other special devices that are used in like field testing. So a huge collection of devices and try to get the capabilities out of these devices. So we collect, we attach them to our base station, get the capabilities, and then prepare a model. And then when we save these capabilities, we also try to save it like who is the baseband vendor, then what's the application it's running if it's a phone, if we try to mark it as a phone, then what kind of like 3GPP standard release it's running. So we try to mark all this information and then store it. So once we have that, we started to like find fingerprints of this inside these capabilities. So if we look clearly, because the first target was like trying to identify who is the baseband manufacturer. So we found some specific capabilities that are, for example, if you take like EIA0, it's a null integrity algorithm, and it's always disabled in Qualcomm-based chipsets. And then the rest of the manufacturers like always have them enabled. I mean, there's no specific reasons like why this is being done. It's kind of like optional to have this feature. So some might implement, some might dynamically enable this feature. If you take like the extended measurement capability, this is always enabled in MediaTek-based chipsets. Then the rest of them just disable it. Maybe they don't need it, or they're not using it. So these are like some fingerprints that we found that actually allow us to identify the baseband. So once you know like who is actually doing this baseband, who is the maker of this baseband, then you just go to the wiki and then find out like who is exactly or which devices are exactly like using this chipset. There are like so many chipsets you'll find like Snapdragon 700 or Kirin 980 from Huawei. So there's a lot of information there which gives you which kind of devices are exactly using this one. So we are like halfway now. We know like the baseband model, maker, then now the goal is to like identify the right device and then the type of application it's running. We could actually separate easily between cellular and then cellular IoT devices, Then difference between phone and other devices, like I said, voice and codec capabilities are always enabled in phones. They are disabled in like USB sticks, laptops, or any other kind of devices that don't need call capabilities. Then there are some tricks, like always Huawei basebands always use Huawei, so this is like they are paired. Like Samsung phones always, they could also use like Qualcomm basebands, but some specific Qualcomm phones always use like Samsung baseband. And Apple, they only stick to 2 of them, either Intel or Qualcomm. So we found it was a bit tough trying to find out like the difference between iOS and Android. So there are like certain GPS capabilities that are always enabled in Android, but always disabled in iOS. And then some voiceover capabilities which are always disabled in iOS devices. I mean, we didn't go to the vendor and then ask like, why is it? They might come up with different reasons, but yeah, we don't really want to care about that. So we just want some features that are like reliable so that we can actually differentiate between both of them. In certain cases, like you might face, depending on the SIM card, for example, like you plug in a SIM card, that might trigger enabling or disabling of some capabilities. So SIM card could be a tricky thing that might give you false results. You have to be careful with that, because like our list of devices like also include devices from Korea, China. So the implementation is slightly different from there when you compare to Europe. So we try to make a huge model so that we are not ending up with like false results. So what's next? Obviously, like we'll be surrounded with like billions of devices. So it's actually fun to actually identify what kind of devices and what kind of like operating system it's running. And also like we have some more techniques like to actually identify the version of the operating system. But we're not presenting it here, but like maybe we can discuss offline. And then we are actually interested to share these traces or the kind of like huge model we have and the automated tool that people could use and then try to play with it. So the second one is the bidding down attacks. Basically, this requires a man in the middle. So we have seen like different bidding down attacks like previously in like bringing the user from 4G to 2G, just sending a message, and then it directly brings the user down to 2G. So we tried something different with these capabilities. We actually like hijacked these capabilities. So we saw that the capabilities are sent prior to establishing security. So this is also a kind of implementation that we saw in many operators. So what we do is like, we act as a man-in-the-middle relay. So when the phone is sending the capabilities, we try to modify some of the capabilities and then forward it to the network. So in this case, neither the device nor the core network has the ability to detect that the capabilities are modified because there is no security or kind of like integrity protection which is detecting this. So that allows actually a success for the attacker. So what exactly we're changing? So that on the right side, like it's a trace from one of the test phones we have. So if you look, like the capability inquiry is done prior to establishing over-the-air security, which gives the upper hand for the attacker. So what exactly we are changing in the radio capabilities? We are trying to modify the category of the device. Like if it's a Cat12 or Cat16 device, try to set it to Cat1 device. So like I said, Cat1 device is something like very low powered. It actually represents an IoT device. And we are also trying to disable some features like carrier aggregation or MIMO, because like these are essential to receive the speed on LTE network. Or else there's no, I mean, if there are no such technologies, like there is no difference between a GPRS phone and an LTE phone. So these are essential. Then frequency bands, obviously, like when you're traveling, maybe different base stations support different frequency bands. So it's important that the phone supports at least some bands. Maybe 5, 6, 7, 8, 9. So, but what we try to do, we try to remove these bands, telling the network that this device do not support, maybe it supports only one band or one type of frequency that which we are operating now, and try to remove the rest of the frequencies. Then we also remove the voice over LTE, which is the traditional way of making voice calls on LTE. There is also a fallback mechanism. Because if you receive these capabilities, it means that the phone supports, or if the phone has to make phone calls, it has to go back to 2G and then make the phone calls. So we try to remove all these capabilities and then send it to the network. The network accepts it. everything is great. So the phone is actually connected now. But the phone is actually connected now to the network like an IoT device. It's not connected like a real iPhone or like. So we tried to do some tests with, I think we had that time was like iPhone 8 and then also some routers which are mostly based on Qualcomm's. So it doesn't mean that these are only, this is the problem in the specification. So this affects any kind of baseband. So some of the results or the impact of this is like the data without the attacker, the speed of the data connection was somewhere around like 48 Mbps. I mean, theoretically, an iPhone 10 is supposed to receive speeds like 500 Mbps or even more, but practically, like we don't see that speeds in commercial networks. I think when we are playing in Germany, like I think we saw 50 Mbps when it was like peak hours time. So what we see after the attack is like the speed is reduced to 2 Mbps. It can also go down depending on the amount of traffic that's there on the network. So for voice or LTE calls, the device is being pushed to 2G. It has to go back to 2G and then make the voice calls, and then again it will come back to the network, the LTE network. So this is some of the effect of doing this. So you're actually attaching a smartphone like an IoT device. So you're actually killing the speed and some of the essential services that are actually supposed to receive on LTE. We tried on the same experiments on like 32 networks, like different parts of the world, and we see that this kind of behavior where capabilities are actually requested or exchanged prior to security in 22 networks, but the rest of the 10 networks are actually asking for the capabilities after establishing the security. So the attacker cannot actually modify. If even he modifies, because there is kind of an integrity protection, it will be detected by the network. So there's a problem. And the nice thing here is like the capabilities are actually stored on the core network for like 7 days or until you restart your device. So for all these 7 days, like the phone is acting like an IoT device. So even if you are traveling in the city, you still don't receive the speed you want until you restart your device. So why, you might ask this, like, okay, what's the reason? Like, why do you want to get the capabilities before security? So this could be something for optimization purposes, because like operators want to just check what kind of like radio capabilities the device is supporting. Based on that, they want to optimize some radio features and then go for the security. The third one was the battery drain attack, which is actually dedicated for IoT devices. So the same style of attack, we try to modify, being a man in the middle, we try to modify the capabilities. But if you look, maybe you must have heard in the market, like, okay, the device operates on 2 AAA size batteries for like 10 years. So you don't need any kind of like attention for the device. So these are something like narrowband IoT devices. So they have some feature called power saving mode. So basically, the device attaches to the network. It says that it has this power saving capability, and then it sends some bits, and then it goes off, actually. The device is like literally off, doing nothing. So in this case, being an attacker, when you modify this information, telling that this device doesn't support any kind of like power saving mode. So what happens in this case, network thinks that this is a normal device, and it wouldn't like send back the power off command to the device. So basically, the device is on for all the time, and then it's actually draining battery. And then maybe within like 5 days, you can actually drain the whole battery, because normally like the phone, when it's on, it's obviously like listening to neighboring cells, like doing some power measurements. So when it keeps doing all this stuff, it's draining battery, and then you're actually killing the device. So how to restore from this? It actually requires a restart, because it has to do the attach again to the network and tell that it's actually an IoT device and not any other like a phone. So these are like some 3 types of attacks like we tried on the 5G access protocols, and the next one would be taken over by Ravi.
Yes, so this was the first type. So this is basically, and he mentioned most of the time 4G or LTE, because the point is we don't have the real network or 5G to play it on. But the standard documents which has been improvised from 4G to 5G, so these things hasn't changed at all. So this is the same thing. And what he mentioned about the IoT attacks, I mean, this has been informed to the 3GPP who designed the standards. There were many operators also involved for the discussion, and they discuss and they recognize this is the problem for some of the problems with IoT or some security issues, and they had fixed it. So it's in the standard, but this will not come into the early version of 5G devices. So this may take some time. You get it until they fix it. So this was the first type. You can exploit the unprotected data or unauthenticated data which is coming on the broadcast channel of mobile or IoT, mobile and IoT devices. Now, second thing is now after you still can exploit this one. Now we go next step further. So this is basically exploiting a little bit unprotected data, but this is about authentication. So this is not the radio, but this is now we are going on layer 3 now. So this is the information what you see on layer 3. So what has been known in the past, we know that the IMSI Catcher works on identifying the mobile phone based on the IMSI. IMSI means your SIM card has a unique number, and actually they recognize by you this number. So this is what exactly you know. And this is, everybody knows how this IMSI Catcher works in 2G, 3G, and 4G. And now in 5G, it will no longer work because your IMSI is no longer in plain text. So it comes after the encryption. It's using a PKI infrastructure, and then it's secured. So no longer passive encryption really passive IMSI Catcher will not work. And we also had a problem with the challenge of the protocol. They also been exploited. So what exactly new we had? So basically, we exploit the authentication material which we received from the mobile operator, and partly with resynchronization attack. So this looks like a complicated. I have a short period of a time, but just to give a reference, what exactly this is, just to give a simple explanation. If I start my phone now, what happens? My mobile phone sends request to the tower. Let's that Telia, it sends request to Telia. This is the guy who wants to authenticate. Do you know this guy? The Telia says, okay, this belongs to me. This has my SIM card. So let's authenticate this guy. So the Telia sends two messages, two bits, which is called R for random number, A for authentication token. So 2 bits come from the network to this phone, and this phone has to verify whether it has the correct AUTN or not. So it does some computation, some magic. Don't ask me right now. I ask later. I don't have time. So after this checking, it says that, OK, this is the right guy, so he can call now. So what attacker needs to do for me, I just need to record one time an AUTN message, only one time in a lifetime of a mobile phone. Lifetime of mobile phone. I just need a one message, OK? If I get this message, that's enough. So what I do in the magic then, I just need to replay this message anytime I want to track this guy in area. So if I replay R and AUTN, now I just explain a little bit math here for you. So what exactly this AUTN is basically is called C into a MAC value. Let's assume C and MAC. So what exactly this a MAC basically is a function of some sequence number. Sequence number means whenever we send a new sequence number, it stores your sequence number like sequentially, and it's like a nonce, but it has been incremented by one value. So they need to keep track what exactly the problem happened, and then this C1 is equal to sequence number XOR with AK. So AK means what? This is anonymity key. So your sequence number is encrypted with anonymity key, for example. If you know the sequence number, you know the right target. For example, Altaf's phone and my phone has a unique sequence number value which gets incremental every time my phone authenticates. It's like this. Simple. Nonce get incremental by 1. So you need to protect this nonce. Attacker should not be able to listen. And if I replay this R and AUTN 2 times, what I get value basically, because I replay the same value. So basically, I will generate the same anonymity key, AK star. If you see on this blue one, AK and AK, these 2 values. So what happens if I do a simple math of like this AK and I replay the same value after like tomorrow to this mobile phone, it's gonna give me sequence number 2 because sequence number has been used. I use phone for a couple of times, but the AK will be same. And if I just XOR those 2 values, what I get sequence number 1 plus sequence number 2. So this is like a classical XOR problem in the design of a protocol that you just cancel the values and you get sequence number 1 and 2. So we did some kind of a computation and tried to find some formula. Can we recognize this sequence number value? So we need some kind of, let's say, 32 authentication vectors which we can fetch from the operator. And actually we can perform the computation and we learn the 7 least bits of the sequence number. So and this allows us to uniquely identify a particular user. Because every user has a unique sequence, so I can really say that these phones belong to Altaf. no matter wherever he goes, because I can again recognize this sequence number value. This was a problem in the design of the protocol or cryptologic. We also informed the standard body. Basically, this allows us to identify certain users. So this is still IMSI Catcher. We are trying and locating, but not based on the IMSI, but exploiting the design, I mean the cryptologic on the protocol. A little bit complicated, but still this is good for targeted attacks, not for a massive, like a mass level passive attack. So this is still classified as a targeted attack if your target is really known. So all these attacks has been informed to 3GPP, GSMA. They assigned some CVD, and they are about to fix some issues. There is ongoing discussion going on because they mentioned this is targeted attack, so they gave it lower priority because it doesn't need to be fixed right now, but we'll fix in future. So maybe until it's some time or whatever it is. Yes, and so we have almost 7-8 minutes. So I will just summary. We'll covering that. Okay. Hope with the time we managed you to convey the problems, what we've been looking to, but also I will end on this one element or note where there is a report from NATO which talks about 5G. Now this is what we talk about the radio problems because we are heavily looking from since last couple of years on radio side, so we have pretty good expertise and we tell, but we little look on the core network, okay? This is an explore area, which we told we. But now we are moving towards 5G where everything is virtual, gonna be on a cloud network, and people trying to see 5G as basically an emerging signal intelligence platform for collecting and processing telemetry data. Even if it's encrypted with end-to-end devices, I mean, literally, you're gonna have a telemetry data which can still identify particular user or device or something like this, and this is more critical to identify. And that's what this makes more interesting, the new transformation of moving towards the cloud, adopting internet-based protocol to the core network. Of course, it's good to adopt, but there has to be a proper separation as well. And on this end, we end the talk and open for some questions. I hope we have 5 minutes and we managed to finish in a short period of time.
Absolutely, thank you very much.
If question comes or something, we have this demo for Akka attack, but I think we can explain you or offline we can show you if we don't have enough time, so we can skip it.
We have like 5 minutes. I mean, people want to ask questions.
Yeah.
I know it doesn't matter what questions I ask, because I know as soon as we put this online on YouTube, the only question in the comments is going to be like, well, isn't 5G just a mind control thing? I heard it from a reliable source of a friend of mine.
Okay.
No, but do we have questions from the audience? No? Do you want to show it?
Okay. So this is about the second attack, what we did with the SIM card. So how do you really calculate those values in basically? So what we're doing is basically now how we track. So here, we don't need a IMSI as I explained. So many people ask, how do you really get IMSI? But this was about the 4G. How many people really use HLR lookup services? HLR lookup services, do anybody know? Actually, in the past time, when you just put the mobile phone number into HLR lookup services, it used to give you IMSI back. And that's like enough to get all the authentication token of your target. That's it, game over. So once you get the IMSI, and then you just get all the authentication vector of any user in the world. I don't need to be in the proximity or anywhere. You just get unlimited authentication tokens to compute the sequence number. So this was the best way we had. But nowadays, every mobile operator is trying to reduce the access to this HLR lookup APIs, for example. So yeah, so basically, this is one way of getting it. Then we try to assume that you get this IMSI or identifier, for example, or something. You just buy a dummy Chinese SIM card, for example, and you put that target number, IMSI, into the SIM card. You reprogram it. And off you go. You have this now dummy SIM card of your target. Now you just need to put this into your mobile phone. And let's assume that you are doing this in Japan somewhere and you wanted to target Altaf now. But now you need authentication tokens. So now this guy is doing everything in Japan. So he put this dummy SIM card in his phone in Japan, and he's trying to say that I want to authenticate behalf of Altaf. So what it happens, he will not able to authenticate, but he's going to get this random number and authentication token 1,000 times, no limit, anything. So he will just collect all these tokens for n number of a time. And that's what he need to collect those tokens to able to compute the sequence number. And when he comes to close to Altaf, let's say in the proximity of 2 kilometers to track whether he is here or not. So he just fire up his fake base stations and try to send this collected random number and authentication token to his phone, trying to identify whether Altaf is here or not. So he will just send those tokens in the air, for example, and this is what now this fake base station is sending to the 4G phone. This is just to tell you the difference between Altaf's phone and Matthias' phone, what exactly the difference between these two phones, for example. Now we look at the data, and it shows some unique parameters, for example, there. So when Matthias' phone is trying to connect to our base station, what happened actually we will see. So authentication fails because we don't have any data about Matthias' phone, and basically we are already failed there. So he's now injecting some more data to just see what response we get. So what exactly happened is that it gives me a MAC failure. MAC failure, it already says that this is not a replay data. It says that this doesn't belong to Matthias at all, this authentication vector. So this is his wrong target. But when Altaf's phone received this token, then we get a different error message, and we will see. This is also enough to recognize between two phones, for example. So now Altaf's phone will give a different response in this case. So we are sending same data again to Altaf's phone. Yeah, now we are feeding again those authentication tokens, AUTN and RAND, and we get a response saying sync failure. So it's the same mobile phone of Altaf, but it's saying that this token has been replayed again. That's what we have, a sync failure. Now we need to synchronize that. We need to avoid this replay. And that's what actually this phone is giving me its pass sequence number, which encrypted with anonymity key or something. And that's enough for his response. So his one response is enough for me to calculate this sequence number for us, for example. And this is what then we do offline. Then we have the algorithm which we design. And this is what exactly we identify a victim based on this failure. And again, the range of attack could be different. The way you design your antenna, of course, you want to cover a 500 meter or 2 kilometer, the way you do, for example. And this is basically the response. You have a sequence number and AQ. And now we try to compute like this kind of value we get. And this is pretty unique per user. We tested many mobile phone, many SIM cards of different European operators, and actually we uniquely identify the user. So this is what exactly tells the difference. And why this is unique for 5G, because in 5G, this mechanism hasn't changed at all. They added the public key encryption for protecting the IMSI, but the underlying mechanism for authentication, MAC failure, sync failure remains as it is. This is common for 3G, 4G, and 5G. And that's what we say actually our attack is applicable for 3G, 4G, and 5G techniques, 5G networks, for example. All right. And that's it, and this is the same for 5G. And this is also informed to the 3GPP body, and I hope this is being currently discussed whether they should address or not, for example.
We do have one question over.
Yes.
Yes. You showed us the downgrade attack. You showed us a couple of countries where it was tested and proved. Have you tried it in Sweden?
Yes.
Does it work?
Yeah. So there's a difference among operators. So I wouldn't say like all of them are implementing the same way. So there was a difference between, I think 2 operators are doing in one way, the one in another way. So like I said, there's a difference in the sequence. So yeah, the same thing in Germany. So one of them is following a good practice. The other's actually not a good practice. So but this is, I think, well-informed operators now. So I don't know like how much effort it takes to actually correct this. Because like there are, so we have this like 2 types, either it's a configurational flaw or whether it's a direct implementation flaw. And it takes more effort, I guess, with the implementation to correct it. Or, yeah, I think we will check again after like 6 months and then just to see if things changed or not.
But I think there are some clear guidelines given by now by GSMA to every operator, and it's their decision to modify their settings. And when we talk to a few operators, they were surprised, what is this? Because they just rely blindly on the vendor of provider network. They just have everything default running. So they have no idea what's going on. So there are some operators like this. So there is no idea what's going on there for them.
Okay, thanks.
Oh, get a hand over there.
One question. You mentioned that 22 operators sent the capabilities in clear text, and then 10 had the security turned on. What is the rationale of having it turned on? And is that an operator setting? Is there a financial cost to having it turned on? Just trying to understand the reasoning on why having it in clear text versus having it turned on.
I think I just answered this. Many operators doesn't know at all, so they have no knowledge about this. So there are very few good operators, especially in Europe. US, I can't say because we haven't done many testing in US. So the guys are good enough to understand the implication of this. So they ask vendors to modify those things because they have the knowledge. And these 22 operators, Asian and somewhere, they have no knowledge about what's running, what is the configuration of the network. They have no idea. That's what is running by default. So maybe we told the GSMA it's a good practice that you ask operator to check the default settings or give the guidelines what should be default. So maybe the vendor like Ericsson, Nokia should give default enable. So why disable? But sometimes you need those reports from the mobile phone, why it's crashing. So you need those reports or why this has been behaving like this. So you need those UE capabilities or measurement report before as well. So it's again trade-off the way they do, for example, in that regard.
Finished with questions? More questions? All right, thank you, Ravishankar and Altaf.
Yeah, thanks.